Hello. For the Week 14 video project, I will be discussing, proving, and later explaining through examples Theorem 4.6.3 in the book, otherwise known as the plus-minus theorem. So the basic definition outlined in the book, let's say we have S be a non-empty set of vectors in a vector space. Our A says, if S is linearly independent, and if V is a vector in V that is outside of span S, then the S union with V that results by inserting V into S is still linearly independent. If V is a vector in S that is expressible as a linear combination of other vectors in S, and if S minus V denotes the set obtained by removing V from S, then S minus V span the same space. We are then left with span of S equals the span of S minus V. What we have in this theorem are conditions that explain when you can add a vector to a set and when you can remove a vector from a set without messing things up. So in this way, this theorem has two parts. The plus part, and the minus. So the first part, adding a vector to a set. When adding a vector, we must keep in mind if S is linearly independent and vector V does not belong in span S, then adding vector V keeps the set linearly independent. Now, here we start with the set S that is linearly independent. We then want to add a new vector V. If this new vector is not a linear combination of the vectors in S, then adding this vector keeps everything linearly independent, meaning this set stays independent. Now, the minus part that I referred to explains when we want to remove a vector. Let's say if we have a vector v and it belongs to S, and it is a linear combination of the other vectors in S, then removing it does not change the span. Now, let's say your set S, whatever set it is, has a vector v that is redundant, meaning that other vectors in this set can already produce it. Oops. What this allows you to do, you can safely remove this vector and the span will stay exactly the same. Yeah. Here's some basic examples. No, we'll call them mini examples to help demonstrate these ideas. This first example, we're going to add a vector. Say we have a set S equals 1, 0, and we want to add vector v, which is 0, 1. We have to note this is outside the span of S. What we get, the result will be independent. But if we want to add vector v equals 2, 0, which is in the span, we lose independence. The second little example, we're going to remove a vector. Let's say we have a space S equals 1, 0, oops, 0, 1, and 1, 1. We see that point 1, 1 can be made by adding 1, 0 and 0, 1. We then know we can remove 1, 1 because we know that these points already tell us enough without needing 1, 1. So we get the span, and when we remove 1, 1, we get the span of 1, 0 and 0, 1. And we see nothing changes. So, to summarize, when we want to add a vector, we must make sure that the new vector we want to add is not in the span of S. And what we get is that the independence is preserved. And if we want to remove a vector, we must make sure that the vector we want to add is in the span of the rest of S. And we get the span does not change. So again, this minus part of the theorem, when we want to remove a vector, we see that if V belongs to S, it is a linear combination of the other vectors in S. Then removing it does not change the span. Exactly what we said over here. Oops. So now we're going to prove. So we will proving the adding portion first. So we want to show that adding a new vector V, let's say, that is not in the span of S keeps the set independent. So we know that a set is independent if the only solution to C1 S1 plus C2 S2 plus CK SK plus CV equals 0. If the solution is C1 plus C2 plus CK plus CV equals 0. Now we can assume a linear combination C1 plus C2 plus CK equals 0 and show all coefficients must be 0. Now, when we subtract CV from the left side, we get C1 plus C2. Sorry, yes. C2 plus K equals negative CV. What we get is that the right side is now a multiple of V, and the left side is a combination of vectors in S. Oops, I forgot to write the S1. Now, if C does not equal 0, we can solve for V. And what we get is V equals negative 1 divided by C times C1 S1 plus C2 S2 plus CK SK. What we have now and what we can see is that V is now a combination of vectors in S. However, this contradicts what we said earlier when we said V does not belong in span S. So C cannot be 0. Therefore, the equation becomes C1 S1 plus C2 S2 plus CK SK equals 0. And since S was already independent, the final solution becomes C1 equals C2 equals CK, which equals a 0. And because all coefficients must be 0, S in union with V, set S together with V, with vector V is linearly independent. Now, the proof when we want to remove a vector. When removing a vector, we want to prove if V is a combination of other vectors in vector space S, and only then do we know removing oops, vector V does not change the span. So the first step is we want to show that span S includes span S minus vector V. Every vector in the span of S is made from combinations of the vectors in S. Highlight that. Let's say we're given vector VR, which equals A1 S1 plus A2 S2, because we assume V is a linear combination. We assume this so that anytime a linear combination uses V, we can replace VR with this expression. And what this allows is the ability to build with or without VR. So removing it keeps the full span. So let's say you have a vector, or let's say you have vector W in span S, which equals A1 S1 plus A2 S2 plus AR VR. Oops. You can substitute our value for VR up here into here. So what you get is W equals A1 S1 plus A2 S2 plus AR times A1 S1 plus A2 S2, which then gets W as a linear combination of S1, S2, SR minus 1. So essentially what you have is when you remove a vector that is repeating what other vectors already do, it allows you to remove it without having to lose anything. So let's go through these examples. This first example, we're going to add a vector. So let's say we are given a linearly independent set in R3. S equals 2, 1, 0, and 1, 3, 0. And we want to add a new vector, 4, negative 1, and 5. So combining vectors in S, we get A times 2, 1, 0 plus B times 1, 3, 0. And what that gives us is 2A plus B, A plus 3B, and 0. The third coordinate is always 0, as we see here, but the vector we want to add has a third coordinate of 5 up here. Since you cannot get a 5 in the third coordinate from the set S, 4, negative 1, and 5, it is not contained in span S, which satisfies the plus theorem condition. And because we see that, we can conclude that set S containing 4, negative 1, and 5 is still linearly independent, because we see that the new vector is not in span S. In this example, we're removing a vector. So let's say we're given a set S equals 3, 2, 1, 6, 4, 2, and 1, 0, 0. We notice that this point 6, 4, 2 can be obtained by taking the first point 3, 2, 1 and multiplying it by 2. What this tells us is that given that we have already have the direction vector 3, 2, 1, this already tells enough information. 6, 4, 2 essentially adds nothing new. So removing it would not affect the span. So removing it, you get S minus 6, 4, 2, which leaves you with 3, 2, 1, comma, 1, 0, 0. What this means is that the new span S becomes span of 3, 2, 1, and 1, 0, 0. This is exactly the same as the smaller set and satisfies the minus theorem condition. So the vector 6, 4, 2 can be safely removed because it's already expressible using the others. In this sense, that vector was already expressed with these points. So in this first example, we see that the new vector is not in span S, so we see that the independence is preserved. In example 2, we see that when vector S is in span S, when vector V, sorry, is in span S, the span itself does not change.